Tonight, we are happily joined by Dozer. I think you said this is your fourth time attending, so I
Something
like
like
to
that.
keep a good, 4-to-1 attendance to speaker ratio. So everybody else, keep that in mind, especially some of you that have been attending for years. So Dozer is a software engineer turned security professional, perpetual tinker, and keyboard enthusiast. And tonight he will be sharing his journey to create the perfect custom keyboard. From his abstract, do you use a wireless keyboard? How much do you trust it? Probably a little less after this talk. Join me on my journey to create the perfect custom keyboard and how it led down a rabbit hole of hacking proprietary protocols and unexpected vulnerability discoveries. So, before we hop into that, a couple housekeeping items. Number one, if you are not the speaker, please keep your mic muted. We all love cats and dogs. We don't love hearing them during the talk. We spoke earlier. I spoke earlier to Dozer, and the preference for questions is to save them all for the end. So we have a couple options. If you are comfortable speaking, you may save your questions for the end and ask them yourself. Otherwise, if you do not want to speak, you can drop them in chat. I will ask them on your behalf later. One other item of note. Our speaker has requested that he be allowed to record the meeting tonight. So I will give this last warning one more time. This meeting is being recorded by our speaker. It will be going on YouTube at a future date. If you're not comfortable showing your face and/or having your voice heard, please keep those turned off. Beyond that, I think we're just about ready to go. Dozer, take it away.
All right, let's just get the screen share up. All right, should be able to see my screen, I hope. And thank you for the lovely introduction. So my talk here is going to be about keyboard hacking, and I promise you that's more interesting than it sounds. And if you stick with me all the way to the end, you'll get a free 0 day. But before we get to that, let's get into the obligatory who am I? If the presentation will work. There we go. So I'm Dozer, also known as the Crazyo online. That's what you'll find my username in a lot of places. I work for Veritas Technologies, and I started with them as a software engineer, but transitioned into a security role doing penetration testing and exploit development against their products. I've achieved a number of offensive security certifications, the OSCP, OSCE, and OSWE, and most importantly for this presentation, I'm a keyboard enthusiast. But why, I hear you cry, what is there to be enthusiastic with about keyboards? And I'm sure we can all agree that IBM Model Ms and Cherry switches are pretty nice, but I have a particular love of 10 keyless track point keyboards. Uh, these ones I have pictured here are the ones that I own, and they span a wide quality spectrum. The first one is the one I'm actually using right now. It's pretty good. It's basically a ThinkPad keyboard ripped off of a ThinkPad and with a USB cable attached to it. A nice short key travel that I like. USB is not bad. It's got a non-standard layout, which kind of sucks, and membrane switches, of course, and all of these have that problem. The second one's a bit nicer in that it has a standard layout, but fails in some other ways, like using the outdated PS2 interface and the keys jam. The third one isn't even worth talking about. It was built to be e-waste. Its only redeeming feature is that it's technically wireless, but it's plagued with such connection issues that it's not even worth considering using. Never buy that thing. With that being the state of trackpoint keyboards, I thought I could do better. So I set myself the goal of creating a wireless, 10 keyless trackpoint keyboard with mechanical switches, of course, and a standard layout. Now, when I say wireless, I mean not Bluetooth. We've all used Bluetooth. We know the sort of issues it has. There's trouble pairing and constant connection issues. It tries to be a jack of all trades and kind of a master of none. So I made what I thought was the very reasonable decision to use Logitech's Unifying protocol for my keyboard. Now, Unifying has a lot of benefits over Bluetooth. It's purpose-built for human interface devices like your keyboards and your mice. It's technically AES encrypted. You can pair up to 6 devices to a single receiver, and that sounds like a disadvantage, but the pairing is done to the receiver itself and not to the underlying host operating system, which lets it pull off some nice tricks like being able to work in your BIOS, or if you unplug the receiver and put it into another machine, it just works. As far as the computer is concerned, you're basically using a wired USB keyboard. It's got pretty long range. Logitech claims at least that it can work up to 10 meters away. In practice, it's less than that, but it's usually plenty. And in my subjective experience, it reconnects lightning quick. You know, if it happens to get out of range, you bring it back and it's connected just like that. And I've run into lots of places where Bluetooth does not do that. And probably its biggest feature is that it's absolutely proprietary. So if I want to use unifying in my keyboard, I'm going to have to hack it. Thankfully, I'm not the first person to do this kind of research. Travis Goodspeed kind of kicked off this whole revolution in hacking keyboards, in my opinion. He discovered a pseudo-promiscuous mode in the NRF24 series of radios that tend to be used by numerous manufacturers to produce their keyboards and mice. Sammy Kamkar created a device that he called Key Sweeper, which is pictured here. And that uses one of these NRF radios in its pseudo-promiscuous mode to sniff packets and then decrypt and transmit them over a cellular connection back to his command and control system. And he built this to sniff Microsoft keyboard packets, which have a really weak XOR encryption. Then Mark Newland came along with his mouse jack, key jack, and key sniffer research. These discovered a wide range of vulnerabilities from various vendors, and what I cared about, of course, was his Logitech research, where he discovered forced pairing vulnerabilities, encrypted keystroke injection vulnerabilities, impersonation, like making a mouse appear as a keyboard, that sort of thing. And through his research, he created a lot of tooling and documentation on the unifying protocol that was basically essential for my research. But he stopped short of completely reverse engineering the encryption that Logitech devices use. Then Matthias and Gerhard came along with their presentation called Of Mice and Keyboards, much better name than mine. And they figured out how to dump encryption keys out of a variety of different keyboards from different vendors. But once again, Logitech's devices were the only ones that resisted their attacks. So from all of that prior research, I was able to get a pretty good head start on this. We know that unifying receivers and devices use Nordic Semiconductor hardware for the most part. Receivers use the NRF24 LU1, which is a system on a chip with a processor, RAM, flash, and a radio built into it. Devices like your keyboards and mice tend to use the NRF24 LE1, which is a lower energy variant of the same chip without USB support. These chips talk to each other over 2.4 gigahertz RF using the Nordic Semiconductor proprietary enhanced shock burst protocol as a data link layer. Now, the unifying protocol is built on top of that data link layer with payloads sent in each packet, and the majority of the unifying protocol is actually clear text. So we know most of the data and the structure of the data that's sent between these devices, thanks mostly to Mark Newland's research. There is one exception, though, that keystroke packets are AES 128 encrypted. And that's for the obvious reason that if you're typing in your banking details, you don't want someone to be able to sniff those packets and see what you're typing. So that being the only critical transmission, they've encrypted that. So to drive this point home, at the top here we have an enhanced shock burst packet. It looks more or less like TCP/IP, but a bit simpler. The part of it that we care about is this payload section. These packets can carry 0 to 32 bytes of payload data. And what I care about in particular is the unifying encrypted keystroke packet, which is really the only packet that hasn't been fully reverse engineered by prior researchers. Again, the packet doesn't contain, or contains a lot of things that we don't care about, but the bit that we do care about is this 8-byte encrypted data section and the 4-byte AES counter, which we'll talk a little more about in the future. The encrypted data, we don't know necessarily the exact value of it. I mean, it's encrypted, come on. But we can glean some amount of information about its structure from keystroke injection vulnerabilities. And it's been determined that the first byte is modifier keys. These are your Control, Alt, Shift, Windows key, that sort of thing, in bit fields. The next 6 bytes are keyboard scan codes. This is the same sort of information that gets sent over a USB cable. And the last byte is an unknown. And that's one of the things that we have to figure out here. Now, a lot of what we're going to be talking about is focused on AES encryption. So to make sure that we're all on the same page, I want to give a quick and dirty overview of how AES counter mode encryption works. To do counter mode encryption, you need to create an initialization vector, also known as an IV, and that consists of a nonce, which is a random number that never changes and is basically unknown to us. That gets combined with a counter, like what we saw on the previous slide, to form an IV. That IV is then encrypted using a secret key that is shared between device and receiver. The resulting encrypted IV is bitwise XORed with some plain text to produce some ciphertext. Then that ciphertext and the counter can be sent over the air to a receiver. On the receiver end, to do decryption, it's much the same as encryption. Take the nonce that it already knows, combine it with the counter that it received to create the IV again, encrypt the IV with the secret key that's already shared, and then the resulting encrypted IV is XORed with the ciphertext to recover the original plaintext. And there are a few things in this chain that we don't know and we need to know in order to legitimately use the Logitech Unifying protocol. We need to know what the nonce value is. We need to know exactly how it's combined with the counter. Usually it's just concatenated, but that's not necessarily the case. We need to know how the shared secret key is negotiated between the device and the receiver. And of course, we need to know what the plaintext value is so that we can replicate that. Thankfully, if we can figure out the first 3, the fourth one is really easy to figure out because we can just take some ciphertext and decrypt it, and boom, you've got plain text. So I came up with a plan of attack to extract the information that I need, and it's based on the hardware of the unifying receiver. The unifying receiver has a MCU, a multi-point control unit. You can think of it as the CPU of the system, and an AES coprocessor, which handles all of the encryption at a hardware level. And how that works is the MCU receives an encrypted payload. It puts that payload along with the key and the IV into the coprocessor, tells it to start decrypting it. When it finishes, the AES coprocessor sends an interrupt to the MCU so that it knows the decryption is done and it can retrieve the data out of there. And my plan was to take the Logitech Unifying receiver firmware and modify it to hijack that interrupt signal so that when the device receives an encrypted payload, it tries to decrypt it, and when it finishes, it runs my code instead of Logitech's. Then I can reach into the AES coprocessor myself, rip out the key and IV, and write those to the chip's internal flash for later recovery. Now we could test this directly on unifying receiver hardware. It's totally possible to upload arbitrary code to these, but when you start playing around with precompiled binaries, it's really easy to brick a receiver. Ask me how I know. And this is where the Crazy Radio PA comes into the story. This is a little piece of open source hardware that I think was intended to control open source drones, but it runs the exact same chip as a unifying receiver. And more importantly, it has an exposed SPI interface on it. or spy, if you want to call it that. And this can be used to reflash the chip and also read the contents of flash, basically making the crazy radio unbrickable. So I can play with that as much as I want and not have to worry. The fact that it uses the exact same chip and that the entirety of the unifying receiver firmware runs in that one chip means that the crazy radio is indistinguishable from genuine hardware as far as Logitech's firmware is concerned. So you can just put the unmodified firmware directly on a crazy radio and it runs with no questions asked. The last piece of the puzzle as far as testing hardware goes is a bus pirate. This is another piece of open source hardware that can be used to speak all sorts of different serial protocols over a wire, and it supports SPI. So with a little bit of coding on my end, I managed to turn the bus pirate into a flashing device for the crazy radio so I can push firmware and read data out of its flash chip. With all those pieces in place, the attack is pretty simple to perform once I've got a properly modified firmware image. Load the firmware image onto the crazy radio, pair a keyboard to it. As far as it's concerned, it's a normal unifying receiver. Type a little something to trigger the AES interrupt, and then just dump the encryption key out of flash memory. And this actually works. It's kind of astonishing to me when things like this work. We can read the AES key and the IV right out of the chip. The only problem is that these values seem to change all the time in unexpected ways. The IV doesn't seem to contain the counter from any packets that were transmitted. If I try to use these values to decrypt captured payloads, I just get garbage as an output. I investigated a little deeper into it, and it looks like Logitech's firmware doesn't even write to the AES coprocessor in any meaningful way. So I've got to assume that I'm just reading uninitialized memory here, and either they're doing AES purely in software, or they're not doing AES at all, which got me quite concerned. So that's when I decided to contact Logitech support about this, and simply ask them, how is communication between a receiver and a device secured? Nicely, they were able to get back to me and assure me that it is using AES 128. That's great. But since I was already talking with support, I figured, what the hell? I'd ask them how the receiver and device negotiate a shared AES key, because at the end of the day, that's what I really want to know. Unfortunately, they were a little less helpful with that, and came back with, this is a Logitech privet information. The only thing I can tell you is that if you want to use any of our products, you need to use a software or hardware provided from us. So that's a challenge if I've ever heard one. So I need to come up with a new plan of attack to get the information that they won't just give me. So this new plan of attack comes down to the fact that receivers and devices have to store that AES key somewhere. And my assumption is that it must just be sitting in the flash chip, right? Where else are they going to put it? So my plan was to take the unmodified Logitech Unifying receiver firmware, load it onto the crazy radio, plug that into my computer, let it all initialize, unplug it, dump that out so that we have a baseline, then plug it back in, pair a keyboard to it, unplug it, dump the flash again, and then I can compare those two flash dumps, and hopefully any meaningful data will just light up in that comparison. So that's what we have here. In the flash after pairing, there's this big chunk of data here, and that's actually just mundane things like the device's name and its product ID, its RF address, stuff like that. A little deeper into the flash, we find that also a little 6-entry table was created. That table presumably has one record for each device that can be paired to the receiver. And if we look at the first entry, it's got this suspicious 16-byte value. And that could easily be our AES key, because AES 128 uses a 16-bit key. But unfortunately, in doing this, neither the nonce nor the IV really made themselves known. So I need to come up with a second plan of attack. And this is around the time when I realized that if they're doing AES purely in software, then absolutely everything we need should just be sitting in RAM. So why not just reuse the attack from before? Dump RAM, pair a device, type something to make sure RAM has the encryption details loaded into it, dump RAM again, and compare the two. Simple, right? No, not that simple. I can't dump RAM as easily as I can flash. So to actually dump RAM, we're going to need to have a slightly deeper understanding of how the firmware is organized. The receiver firmware starts with this big chunk of code. This handles the normal day-to-day operations of the receiver, receiving packets, decrypting them, generating USB traffic, that sort of thing. Next, there's a little block reserved for device data. This is what we were just looking at in the last flash dump. And after that, we have a bootloader. The bootloader is responsible for performing firmware updates, and the main program gets told to do a firmware update. It jumps to the bootloader. Bootloader receives the new firmware and overwrites the main program without disturbing the data or the bootloader itself. But why do we care about the bootloader? As I've been saying, we can just flash everything directly over SPI, which totally bypasses the bootloader. And this means the bootloader location is a perfect place to hijack execution because we can tell the main program to execute what's at the location of the bootloader at will just by telling it to do a firmware update. So my little dumper takes a pretty barbarian approach, but it's simple and it works. It just reads the entire contents of RAM and writes it out to flash. Then I can unplug the device, hook it up to the bus pirate again, dump it out just like before. And just like that, now we have RAM dumps at our disposal. So I have here the RAM before pairing and the RAM after pairing typing. And in these two, there's only one place where there's a contiguous 16-byte change, which is presumably our AES key. And I'd like to call attention that the RAM before pairing, there's not just null bytes there. There's a little something there. Just keep that in mind for later. A little deeper into RAM, we have a whole host of other seemingly random changes that could be anything. Except this one right here happens to match the AES counter from the last packet that was received by the unifying receiver. And that means that these surrounding non-null bytes are most likely our nonce, and this whole thing should be our IV. So now we have a suspected key, a suspected IV, and an encrypted payload to play with. So all we have left to do is just pump those into the AES algorithm. And when we do that, we get a successfully decrypted payload. It matches just what we would expect to see. We have 1 byte for modifier flags, 6 bytes for keyboard scan codes, and that last mystery byte is always C9 in every packet that's transmitted. Presumably that is so the receiver can tell if it decrypted a sensible payload or not. We still have a little bit of work to do though, because the value we pulled out of RAM is definitely the encryption key, but it doesn't match the value that we pulled out of flash, and we still need to figure out where this AES key came from in the first place. Now, there's too many bytes in common between the key we pulled out of RAM and the value we found in flash for this to be random chance. So my suspicion is that the value we found in flash before is an obfuscated form of the AES key. My suspicion is a little further confirmed by bringing in that value that was in RAM before pairing. If we look at every value that is FF in this, we see that it corresponds positionally to a byte that matches the obfuscated AES key. This led me to believe that the value in RAM before pairing was some form of bit mask. And after playing around with the data a little bit, it's pretty clear that performing a bitwise XNOR between and that's XOR followed by a negation, between the encryption key and the bit mask results in a new value where every byte has parity with another byte in Flash. Now these bytes are all in the wrong order, but that's a simple matter of just rearranging the bytes according to this random sequence. And this random sequence and the bit mask from before are always the same. So at this point, we know how to translate between the obfuscated key and the fully deobfuscated encryption key. And let this be a reminder that security by obscurity doesn't work. It took mere minutes to reverse this. This also means that if you can extract a flash dump from a unifying receiver, you have all the information necessary to convert the extracted information into a usable AES key, and you can dump the flash out of a receiver. So this means that you can obtain the encryption keys. If you have one-time access to someone's receiver, then capture all their keyboard traffic and decrypt it and see all their passwords, credit card numbers, banking information, things like that. So that's a pretty big security problem. Now we still need to figure out where the value that we found in Flash, this obfuscated key, came from, if we're going to use the protocol legitimately. And to figure that out, we just have to look at the pairing process. So for unifying, pairing is done by using the desktop software to put the receiver into pairing mode, which makes it listen on a predetermined address, which is on screen now. Then you power cycle your device, which makes it transmit a pairing packet to that predetermined address. And that packet contains, among other things, its product ID, which becomes part of our AES key. The receiver then responds with a new RF address for all future communications, as well as its product ID. And the most significant bytes of that RF address and the device's product ID also get integrated into the obfuscated encryption key. The keyboard then responds with 4 bytes of seemingly random data, which become part of the key, and the receiver responds with 4 more bytes of seemingly random data that become part of the key. And that's the entirety of the key exchange process. While they've done more obfuscation by splitting it up across different packets and different addresses, it's still just clear text transmission of an encryption key. It amounts to screaming the encryption key out into the void and hoping no one's listening. And I believe that this is why this is considered Logitech's private information, because it's kind of a shameful way of doing it. But it gets even worse than clear text transmission of an encryption key. Because if we think about what makes AES 128 secure, it's key space, right? A typical AES 128 key has 2 to the 128 possible combinations. So if you wanted to crack an AES encryption key, you would have to potentially test every single one of these keys. But like I said, our encryption key is derived from our RF address. And our RF address is transmitted with every single packet that gets sent, making it effectively public information. So if you're trying to crack this key and you do, 1 second of packet capturing, you already know 4 bytes of the encryption key. And this knocks out a bunch of complexity and brings it down to 2 to the 96 possible keys. Same problem happens with the receiver's product ID. Now, every receiver that I've tested so far, which is a few of them, has the exact same product ID. So at this point, you can just assume 2 more bytes of the encryption key, lowering the complexity further and bringing it down to 2 to the 80 possible keys. The device product ID is about as bad. Different devices have different product IDs, but all devices of a given model seem to have the same product ID. So if you're a bad actor and you see, a bank manager using a particular Logitech keyboard, you can go buy that same keyboard on Amazon, extract the product ID from it, and now you can just assume 2 more bytes of your bank manager's encryption key. And with that, we have eliminated half of the bytes of the encryption key. But now let's put some numbers behind this to see how bad this actually is. Your typical AES key has this huge key space still. And I benchmarked my desktop at being able to test 300 million AES 128 encryption keys per second. If we divide those numbers through, we find that cracking a typical AES 128 key would take this many years, which is a large number that I'm not going to try to say. But for reference, that is 12 orders of magnitude longer than the age of the universe. So I think we can probably consider AES 128 secure. But what about the weakened form of AES that Logitech devices are using? Well, we'll put up their much smaller key space. Cracking time stays the same. Anyone? Any guesses? Ooh, less than 2,000 years, which is substantially less than the age of the universe. Now, I want to remind you that this is the cracking time for my desktop alone, while I'm still like watching YouTube videos and stuff. If you're a government, you can knock this out in 5 minutes probably, and if you're willing to go rent out some time on a botnet or just buy some cloud computing, you might be able to shorten this significantly. Plus, you don't need to do an exhaustive search. You're bound to get lucky eventually and find the key early. So I believe that this is well within the realm of crackability for most people. And it basically turns Logitech's security into this. If you haven't seen this before, it's a real as seen on TV product called ID Police, and it's fucking hilarious. It's literally just an ink roller. You guys should look this up after the presentation, treat yourself, and maybe buy one, bring it to DEF CON. I bet it would be a hit. So now I want to show you the fruits of my labor here. Got a little demo set up. At the bottom of the screen here, you'll see my desktop, which is playing the role of a victim machine. In the upper left, we've got my laptop, which is playing the role of a attacker machine. And in the upper right, we have a video recording of what I'm doing in MeetSpace. So I can type on a genuine Logitech device, and it appears on our victim machine. I unplug the unifying receiver and plug it into my attacker machine. Run a big nasty command that replaces the Logitech firmware with one that I wrote, and its whole purpose is to just dump the firmware out of the receiver and then reflash the receiver with genuine Logitech Unifying receiver software. This takes about 20 seconds. And just like that, we have the encryption keys dumped out of it. Plug that back into the victim machine. Plug a crazy radio into the attacker machine, and start packet capturing and using the extracted keys to do real-time decryption of the packets and interpret them into ASCII. So everything that's typed on the victim machine appears on the attacker machine in mostly real time. There's some Linux buffering shenanigans going on there. Now I was going to leave it right there, but in the time since I put this presentation together, I decided to go full try-hard and try to implement Logitech's unifying protocol in C directly. Because if you'll remember, the goal of this whole project was to make a fully functioning keyboard. So a similar setup to before. On the right, I've got the Logitech Unifying software, as well as the Arduino IDE open for debugging output. And in the lower left, a little video of what I'm doing with hardware. So I simply put a receiver into pairing mode, reboot an Arduino microcontroller to make it pair. Pairs almost instantly with the receiver. Now the receiver is going to have a little exchange with the device. It's trying to ask, what's your battery status, firmware version, things like that. I just respond to all of those saying, I don't have an answer to those questions. And eventually the receiver relents and puts us into an active state. And if I select the text editor and push a little button on here, we should see a nice little message come up with encrypted packets being used to type it. So while this works on Arduino, It's not Arduino dependent, and in fact, I designed it specifically to be hardware and compiler agnostic, so you should be able to run this code on pretty much anything that you can attach a compatible radio to if you want to. Get that out of the way. Now going forward, I still need to actually build my dream keyboard because at the moment I just have an Arduino and a Nordic Semiconductor radio wired together. As I just demonstrated, the unifying library that I'm writing works, but it still needs a lot of features added to it and some code cleanup. If I can get that done, I would like to see it integrated into the popular free and open source keyboard firmware projects like TMK, QMK, etc. They're on screen. If I can get all of that stuff done, the real lofty goal would be to write a free and open receiver firmware as well, so that we're no longer tethered to Logitech's code base. And if I can do that, then I would control both ends of the communication channel and could implement some much needed security enhancements into Unifying. If any of this sounds interesting to you, feel free to check out my projects, contribute, hit me up on email or Discord. These links are live on GitHub. We've got the Logitech repository with the decrypting and interpreting scripts, and the unifying project for the current state of my reimplementation of their protocol. There'll be updates to that in the near future, I'm sure. So now I'd like to open it up to anyone with questions. I'll also dump the GitHub links into the chat.
Thank you for dropping those links, and thank you for the presentation. Always love a good combination of making and hacking. We don't know what the ideal ratio is, but this was definitely scratching some itches here. No questions from myself. Any from the audience? Anybody want to drop questions in chat? I'd be happy to ask those on your behalf. Otherwise, feel free to just speak up. Question from chat here. Why crack the AES keys on a CPU and not a GPU?
That's a pretty good question and something I investigated quite a bit. Partly because no one seems to have put together a GPU AES cracking program, at least not as far as I've been able to find. Because you go searching around on Stack Overflow and stuff, and all the crypto nerds are happy to tell you that AES is uncrackable, don't even bother, etc., etc. But the little bit of information I could find said that it might actually be faster to do it on a CPU, because modern CPUs have built-in hardware specifically for computing AES encryption. So your processor can do it in like 3 instructions, whereas on a GPU you're going to have to write a lot of custom code and parallelizing stuff, things that I don't really understand. But hey, if any of you want to go and try to write an AES cracker for a GPU, I'd be more than happy to try it out on this.
Any other questions from the group? I guess if I could preempt a potential follow-up to that of like, why not use Hashcat? I'm pretty sure Hashcat has always maintained that they are for hash is. They are not, they don't dwell on encryption.
I've seen people asking that question online, and yeah,
Yep.
Hashcat's response is, nope, we do
Yep.
hashes, not encryption.
Which is, it's understandable.
And
But
I get
it's
it.
also
It's hard to crack AES, so not a lot of people have
yeah.
tried. I'm surprised I've managed to find a utility that I could use to benchmark my CPU in the first place.
Anybody else? We're coming up on about 40 minutes here, so right on time. Good Q&A session. We tend to be a pretty technical group, so I'm not surprised that there aren't. Okay, here we go. Was this sorry, was this only with the USB receiver with the Logitech devices, or also the Bolt USB adapters? Maybe it does not matter.
This is pretty old research. I started doing this before Bolt was even invented, and I just kind of sat on it for a while. So I have not looked into Bolt at all, other than I know that it runs on top of Bluetooth LE, but I don't know anything more than that. I think that would be a great topic for other people to research if this sort of thing sounds cool to you. Um, my guess is that they probably reused some of Unifying's code to build Bolt. So I would not be surprised at all if we find some similar weaknesses in Bolt if anyone tries to do that research.
That sounds like a good topic for a future talk. Okay. Follow-up comment was, okay, I have both adapters and I'm sure corners were cut. Laughing, crying face emoji.
I bet it. I bet they were.